So this is talcum powder, just like baby powder, going down on polyacrylamide, which is basically 99% water, 1% polymer. It's pretty much clear, but it's slightly more viscous than water is. So that means that all this motion that we're going to see is going to be slowed down a little bit so you can actually see it. The soap is going to locally lower the surface tension right in the middle there, and the soap molecules all go to the surface. So the heads really like the water, and the tails really hate the water. So the tails sit outward, and then the molecules of soap all want to move and spread across the interface of the water. Each one has a little meniscus of water touching it. So you've got a particle, and they've got a little meniscus of water that's coming up to it, and then the water likes to minimize the total surface area that there is, right? So bringing those molecules, those particles closer together, then they can join together and they can have only one meniscus on the outside, and that minimizes the total surface area. So this would work on any air-liquid interface. So you could think of any number of places where air meets water, where this spreading could happen, right? And there are a number of those places in the body. So you think your nose, your eyes, your throat, your lungs. And so in this group, we work with spreading drugs in the lung. So if you add, say that white stuff, instead of being talcum powder, is antibiotic, and you have a patient who has cystic fibrosis who needs to get treatment down into an area of the lung where they don't get air because it's blocked from mucus, then you can actually, use something like one of these, oleic acid or something soap-like, and you can spread deep into the lung. When you want to deliver things into the lung, for instance, you're often delivering a droplet of, an aerosolized droplet of medication onto a surface that is mostly water. So we have mostly water in our lungs. It's water with a little polymer. It's kind of similar to this. And so you want to understand how long it takes for each drop to become part of the bulk. So does it deposit its innards quickly? Or does it stay as a drop and travel as a drop and then deposit? Because if it's going to be different if you deposit the drop and it immediately puts down the medication right there, or if it deposits and then carries the medication and dissolves later.
We want to know where the drug eventually ends up, but because drug is hard to see, we're going to replace it with some very red dye.
And you can see that happens so quickly that there's like turbulent mixing out at the edges. And some of it even went through the surface and is sitting as like a ball down at the bottom there.
As soon as you make a drop of the solution, there's surfactant in this too, the same soap that we've been using in everything else. And it's all around the outside of the drop when we're depositing it. But as soon as this touches the surface, those soaps can move from the drop onto the surface, onto the liquid surface here of the water. And as soon as those hit, you cause these Marangoni flows where you have, because they have a bunch of surfactants in one place, they want to spread out. And the sheer force of that spreading rips the drop apart. And some of it is fast enough that it sinks to the bottom, but some of it is slower and gets sheared off of the drop and placed right at the surface.
There's sort of two types of motion in our work. The first is what we call convective, which is this idea of the soap molecules moving across the surface really, really quickly, or any sort of, you put a force on water, you slap the water and it moves, right? That's convective moving, motion. But then there's this overall slower motion, which just happens because the water is water and it's warm, has some heat to it, and it's going to be moving a little bit, always. It's sort of shivering, right? And that's that Brownian, we call it diffusive motion.
Also, sometimes we're wondering what exactly is the rate of diffusion versus convection.
Yeah.
How far is something going to spread in the lung versus how quickly it's going to diffuse into the actual lung.
Right.
Because we want something to spread first and then actually absorb into the lung rather than absorb and then never end up spreading. So that's a constant question.